we're gonna do our thing. Okay, here we go. Cool. Let's learn some physics. I mean, you guys learn the physics. I'll explain the physics. That's the way we're doing this. Okay, here we go. All right. So we talked about sound, and we're gonna do some more talking about that. And specifically, I want to talk about music because music's awesome, right? So I want to talk about how a guitar works a little bit. And we're going to do a simplistic drawing of what a guitar string looks like. So here's a guitar string. It has two ends to it. And between those two ends, there is a string, okay? And just to explain, we're going to go like, okay, basic idea, makes pretty much sense. And it has, of course, the length L here. That makes sense. And this is going to be kind of oscillating back and forth and creating the sound that we hear. Now, let's talk about a few things that we know about this. First of all, we know that the sound created by this is audible, okay? And just a reminder for what audible sound is in terms of frequency. And I use the word audible here a little bit flexibly because audible sound is kind of like visible light. It's like, well, isn't sound supposed to be audible? How is it otherwise? Otherwise, it's not really sound, right? So I call it audible sound. And we talked about what kind of frequencies are audible. Do you guys remember by any chance what the lowest frequency is that your ear can hear?
Was it
20
20
hertz.
hertz, that's right. So it's 20 hertz is the lowest frequency. What's the highest frequency that your ear can hear?
20,000.
20,000. If
20,000.
you're your age, that works. If you're like old like me, it's a lower frequency, maybe 10,000 or something like that, because your ears, your ears die first, I guess. That's the way that works, So, and your eyes too, you got to get glasses. It's terrible. Anyway, so here's the audible sound frequency range. And related to that, we can also talk about the wavelengths, okay? Because the frequency is related to the speed of sound, okay? And the speed of sound is about 343 meters per second. And for you guys, that's about 1/3 of a kilometer per second. Okay, and last time, I think it was last time, we talked about the fact that you can use this as kind of a shortcut to figure out whether you're going to die right now or soon if there's a thunderstorm, right? Because when you hear the lightning, after you, if you see the lightning and then you hear the thunder, you can count the time between the two events to figure out how far away the lightning struck by dividing by 3 after counting the seconds. Okay, and that's very close to being correct for the correct answer. For them, they're Americans, is about 5 seconds equals a mile. About 5 seconds a mile, 3 seconds a kilometer. Close enough. So the frequency is related to the speed of sound through an equation. We had that last time as well. That V equals F times lambda, and we sometimes put that in an Idiotendreieck like this: V, whoop, F, whoop, lambda, whoop. There we go. Okay, cool. So here's the relationship, and specifically, if we're interested in finding lambda, right? Lambda is V over F. Yeah, good. So we can use that information to find the corresponding wavelengths for audible sound. We can write that on here, maybe in red, and I think we did that last time as well.
It cuts off the picture, sort of like where it says 20 hertz. What does it say for the second row?
What does it say for the what?
Does it just say kilometer?
Here says 20,000 hertz. Here says a 1/3 kilometer per second. I think I'm all on the screen. So if it's being cut out for you, Bella, maybe you've got something wrongly adjusted on your screen.
I just realized I fixed it.
You fixed it? Okay, cool. Cool. Okay, so we can, from this information, lambda equals V over F, we can get the two corresponding wavelengths, okay? So for example, for 20 hertz, 343, divided by 20 is 1.7. This is not a sehr gute, this is schlecht, ja. This is not good. Do we have a better red pen? That is the question. Man, oh man. All right, maybe this one? Yeah, that's a little better. 1.7 meters here. And then if you can also find over here, the corresponding frequency is 20,000 hertz and the corresponding wavelength, we did this last time, would be 343 divided by 20,000, and that would be 0.00. That's really small, my goodness. Wait, I screwed this up. There's a 17 meters. Just checking whether you're paying attention. Ha! Ah! That's really funny. I love that joke. Okay, so here we go. So audible sound varies in frequency from 20 hertz to 20,000 hertz. It also varies in wavelength from 0.017 meters to about 17 meters. Okay, and of course that means we got to change these signs in terms of how they're pointing the other way around. So audible sound is greater than 1.7 centimeters and smaller than 17 meters. Okay, you guys cool? That makes sense? Okay, awesome participation. Really enjoyed that. That was fun. Okay, so this is the range here. That's the range there. And of course, we can also have sound that is beyond or below this audible range. Okay, and we have a word for that in English. So for beyond, so for example, or if you are a fan of a soccer team and you are beyond the normal range of how fans behave, what do you call yourself?
A super fan.
No, that's cute, but wrong.
Fanatic.
Oh, you guys really don't know? Fan actually comes from fanatic, so that's actually wrong because fan does mean fanatic. So that's where that word comes from. A fan, a soccer fan, is somebody who's a fanatic about soccer, or as Deutschland Leute, or in British would call it football. Yeah, so, but you guys really don't know? Are you serious? What do you call the crazy soccer fans who, like, you know, set like stuff on fire?
Hooligans.
Oh, cool. That's kind of right, but it's ultras. Ultras. So the ultras are the people who are like really nutso about their Fußballverein. So that's why when we talk about beyond the sound, we are talking about ultrasound. Okay, you've heard that before, I think. And ultrasound refers to frequencies that are above 20,000 hertz. Okay, and you can use ultrasound to actually for medical purposes. Now you can't hear it, obviously. Okay, but you can use this to look into people's bodies because it actually works well with reflecting back off soft tissue, such as a baby in a woman's belly, okay? Or other things, like if you want to take an image of somebody's kidney or somebody's bladder, you can use ultrasound as well. And some of you might have had an ultrasound at some point because doctors wanted to look something at you inside your body. That's what an ultrasound does. It uses frequencies above 20,000 hertz. It's not audible. It's really still sound in the sense of them being the same kind of waves, but they're not audible, so we call them ultrasound. Okay, cool? Cool. So there we go. Now, that was kind of a review of what we did last time. So let's come now back to our guitar string and think about the sound that we have there. I'm going to take a quick picture so I can post that for you later. There we go. Here we go. All right. Oh, That's cut off a little bit there. I'll go doop, 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 doop. Okay, here's the equation we have just a second ago. We had our Idiotendreieck. I'll write it up here again. V, F, and lambda. And when we're talking about music, we don't normally talk about frequency of the sound. We don't say that this or that has a different frequency. We say that has a different, what we call it?
Pitch.
Pitch, that's right. So in music, pitch is kind of the same thing as frequency. Okay, although pitch is kind of the music term and frequency is the physics term. Okay, so let's talk about the pitch of your guitar string. Now, you can vary the pitch, or you can get different pitch for your guitar string by different methods. And there's really three things that affect the pitch of the sound that you get. Okay, and you guys tell me how you can vary the pitch. And I should call on somebody. This is Gala. This is a participation situation, I think. So let's ask, I don't know, let's ask Bella, because she was first here. She gets to get picked first. Bella, how do you change the pitch of a guitar string?
You turn one of the thingies.
The knobs, a little at the end, right? Okay, super, cool. So at the end of this thing, you've got this kind of thing that and it kind of tightens or loosens the string. Agreed? Okay. So what you can do is you can vary the tension. What affects pitch? Question mark. And we're talking specifically about a guitar string or a piano string or a violin string. All these work on the same principle. So you can vary the tension specifically. Oh, we should also write it out in front. That'd be good. So that's kind of messy. Okay, there we go. Good. So tension, FT. And now, if we increase the tension, if we make this thing more taut, okay, we basically increase the tension. What happens to the pitch, Bella?
Wait, say that again, sorry.
So if I tighten the string, increasing the tension in here, what happens to the pitch? Does the sound go up or down?
Oh.
Okay, I think that was an up. That is correct. So the pitch increases if the tension increases. So you increase the tension. This is just an observation. We're not explaining why this is the case. We're just observing that this is true. So if you increase the tension, you increase the pitch, you increase the frequency. Okay, good. Now, second possibility. We have three. I already gave that away. So let's pick on a second person. Jofi was here second, I think. So Jofi, how else can you vary the pitch of your guitar string? What else can you do?
What is that one? The F one?
The one that Bella said was she increased the tension in the string by turning the little knobby thingamajiggers at the end of the neck of the guitar, tightening the string, which increased the pitch. And of course, you could go the other way and decrease tension, lowering the pitch as well. That would work as well.
Yeah, you could do that.
Yeah, but we're looking for something different, so not changing tension. How else could you affect it? Have you ever had a guitar that you had in your hands?
Could you change the density of like the string, like how?
Good. You could change the density of the string. So if you have a guitar or you own a piano, you might know that the strings are actually different densities. You have some that are made of nylon generally, okay? Or if it's some fancy violin, it might be made of some kind of like sheep's gut or something like that, something that's pretty light. And then they also have, on some instruments, actually steel wires that are used as the string, okay, that are very dense. And what we mean by dense is, we mean in this specifically the mass density meaning how much mass do we have per length? So we look at this thing and say, okay, our string has a certain amount of mass for the length of string that we have, and it has a certain length, and that density can vary. And how does it vary? Now, tell me this, Jolfi. The thick strings, the ones that are made up of steel, do they have a pitch that is lower or higher than the pitch of the, it's lower, exactly. So if you increase the mass density, okay, the frequency decreases, okay? Because lower means lower pitch means lower frequency, because pitch and frequency are related.
Yeah.
Okay? Good. Okay, good. All right. Now, there's actually a third way that might be the most obvious way. Which is the third way? Let's ask Guy, how can you change the pitch of the guitar string that you're plucking? You're plucking this thing. Bum, bum.
By the position.
Position. I think you said the position of your hand, right? Yeah, exactly. So you have on here something called a fret, okay? And they're all over the place, but let's just kind of put a fret right in the middle, like that. Okay, this is called a fret, which is like a little piece of metal, okay? And what you can do is you can push on the string like this, yeah? So, boom. Now I'm gonna push it down, and they'll go, boom, boom, boom. Okay, get the idea? That sounds, okay, my singing is terrible, I get that, but in principle, that's correct, right?
Mhm.
Okay, so we see that if we actually take our string and change the length, we can affect the pitch. So for example, bum, 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 okay, makes sense? So we change the pitch by changing the length. So as the length increases, okay, you're gonna have to listen to me one more time. This is about right. Bum, 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 something like that, right? So as you increase the length, what happens to the frequency? What happens to the pitch? Does the pitch go lower or higher if you increase the length?
Lower.
Lower. Good. So this is the relationship we have right there. So the frequency goes down if the length increases. Okay? Does that make sense so far?
Yes.
Good. Excellent. Excellent. Okay. Couple things about that. First things first. Now, taking a look at this thing here, we have this string, okay? And we talked about three properties: the tension, mass density, and the length. Two of those are actual properties of the physical environment. What I mean by that is we have a string right here, and it's made up of a certain material that has a certain tension in it, okay? And whether we look at just half the string or the whole string, either way, the material is the same, okay? So varying the length doesn't change the physical environment, but the other two do, okay? So when we vary the tension, of course we're varying the material, the medium that the wave goes through. When we change the mass density, we also change the material, the medium that the wave goes through. So these two are distinct, okay, because these two change the medium, okay, and this one does not. Now, thinking about what that means for us, well, why does the frequency change? Reminder, the frequency only depends on two factors: the sound speed, the speed of sound in that material, and the wavelength, okay? F is V over lambda. So when we are changing the medium, Which one of those are we changing? Are we changing the length, the wavelength, or are we changing the speed of sound in that material? Let's,
Wavelength.
what's that? Anthony, go.
I said wavelength.
Wavelength, good, that's wrong. So want to guess again?
The other thing.
The other one, good job, good job. So when we're changing the medium, okay, we're changing the wave speed because it's a different medium. You might have heard, for example, that sound waves in railroad tracks travel really, really fast. Yeah, that's like, might be tempting to then go like walk by a railroad track and put your ear on it. Like sometimes they do this in like old movies. They're like, the train is coming, I can hear it. It's thousands of, whatever, you know, you get the idea. But through steel, sound travels really fast compared to air, and it travels really well. So when we change the medium, we change the wave speed. So this is the changing factor there, and we can kind of put that in red, because that is the changed thing in that case. But in the second case, where we are changing the length, right? Now, kind of makes sense. We're going to talk later about how much of a wavelength is actually on here. But when the wave can be on this whole thing, compared to just being on half of thing, of course we're affecting the wavelength. So down here, we're not changing the medium, but we're changing the length, and therefore, not surprisingly, the frequency is equal to V divided by, this is not the best pen anymore, sorry, lambda. So we're affecting this down here. This is what we're changing, okay? So we're changing the length, we're changing thereby lambda, and that affects our frequency because the lambda is changed, okay? So we've laid the groundwork for us to be able to talk more in detail about what the frequency is that is produced by those strings and why. And we're going to get to that next time. I've got some assignments for you guys posted, which is like maybe sad because you don't want to do the work, or maybe happy because you're excited to learn something, or maybe a combination of the two. And I'll just pretend it's a combination of the two. So those are posted. I think those are going to take us to the end of the year. It's about one post a week. And I'm still looking at maybe having a virtual lab for you guys. I was taking it kind of easy on you people because you had all those in-class, in-school sessions. But I do want to make sure we learn some more about music, and also earthquake waves is in there too, which I think is super exciting. So I will now stop the recording.